Alright, hey guys, we're back with part 2 of programming our vector. So let's get into it. So we've done scalar multiplication, adding vectors, subtracting vectors, normalizing magnitude, stuff like that. There's one thing that I want to add before we go any further, and that's the sense of if I'm adding or subtracting vectors, what if they're not of the same dimensions, right? So like say I have a guy with only x and y, 3 and a 4, right? And 5, 6, and a 7, maybe like that, right? I subtract them. Well, it all depends on how zip handles that. And let me show you how zip handles that right off the bat. Let's go shell. Alright, there we go. Okay, so if I do our trusty old list zip, and I just do 1, 2, and then over here I just do 1, 2, 3. You see it just discards the 3 because there's nothing to pair it with, okay? And that in itself is not a very good thing to do when adding them. Because when we do add them, the final result will be in that third dimension. If I add, just say, the 3, 4, and 5, 6, 7, if I add them, I will get that 7 inside the z direction. So what I'm going to do is I'm going to make one thing. I'm going to say while len core is less than 3. We're going to assume all our vectors are up to third dimension here. You don't, if you're doing calculus, you don't really do much more unless you go to like super high level. I'm talking about like for a beginner class. And I'm mainly use this kind of stuff for GPS mapping, so I obviously don't need to go 4D or 5D. So while the length of the coordinates is less than 3, just core.append 0. It's just going to add in zeros, because in reality, 2, 4, 2, 3 now, I guess, because I can't tell you, same as 2, 3, 0. Okay. And if I just put in 2, well, it's 2, 0, 0, right? Okay. So that will help if they're of different lengths and such. Okay? Alright. That's going to be important when we do dot product. Okay? So the dot product is actually pretty simple. If we stick to the function of doing our one-liner little array things, well, and the dot product returns a scalar, if you remember from calculus. It's just we multiply each individual element. So if I have 2 list and it's just 2, 3, 4, and 1, 1, 3, it would just be 1 times 2, okay, and then 2 times 3 plus 3 times 4, right? We just multiply each kind of little pair and then add them together. So what we could do is we could go the sum of all the products in there, sum of x times y, for x, y in self list zip self dot core, and it doesn't matter the order, alright, unlike cross product, which we'll get to in a sec. Self dot core, and then vec dot core. Great. Okay. Alright, so that's looking good. So what can we do with the dot product? Well, we can say a couple things. The dot product, for example, if it's, say, 0, it means the vectors are perpendicular, because the dot product is telling you not only how much of one vector is on it, how much it is on it as a scalar multiple of the other. So it gets you a lot, probably didn't say that, 100% correct, but it basically gives you the part of it that, if I have a guy leaning, there's a part of him, an x part of him. If you've ever taken physics, you see triangles like this all the time, the part of the x velocity and such that's on there, and multiplies it by that. So if I want to say, check if they're perpendicular, okay, I can say return zero, return the value of the expression 0 equals self dot product vec. Now see, there's a problem with that. say we get like 89.9999999, right, which I've totally gotten, or 89, even 89.98, right, you would probably call those guys perpendicular for most purposes, right, like the angle between them is 89.98 or something, you know, like you don't get exactly, you know, the angle between them isn't exactly 90, right. This will return false. So what I want to do is I'm going to add one little thing up here. I'm going to go tolerance equals 0.01, and I'm going to say self.tolerance is equal to tolerance. So I'm going to put in a little tolerance for all these little evaluations, okay? And I'm going to say the dot product, if it's less than 0 plus my self.tolerance, and, because if you said or, here, I'll show you, and 0 plus tolerance is greater than. Actually, I'm going to store self.dot product in a variable, so I don't have to call the function twice, so it doesn't have to repeat the same calculation twice. Vec. I'm going to make this line a bit smaller, too. Alright. So what I'm doing is I'm making like a little range, right? So I'm saying 0 plus or minus this tolerance, right? When it's within the range of 0 plus or minus this tolerance, okay? Then I'm going to just say they're perpendicular, right? If I were to put or here, this, you know, you could probably see where this would go wrong. If it's, you know, because it could be less than 0 plus the tolerance, but it could be like negative, you know, 30 or something, you know, or it could be greater than 0 plus the tolerance, or 0 minus the tolerance, right? But it could be like 50, you know, the dot product, right? So I want to make sure it's within 0 plus or minus the tolerance by checking if it's less than 0 plus the tolerance, and if it's 0 minus the tolerance, right? If it's within that range. Okay, so that's what I'm doing there. Just make sure 0 plus the tolerance. So let's flip my signs here. It's supposed to be less than 0 plus the tolerance, and it's supposed to be greater than minus. What am I doing? 0, and it's supposed to be greater than 0 minus the tolerance. Alright, see, I'm like trying to explain things to you, and there's like a wrong line of code there. Okay, alright. So we can't do parallel yet. There is one way we could do it. And it's the same way we could have done perp. We could have checked for the angle between them. Okay, let's do the angle between them. I'm just going to do angle. And then after these two functions, we'll test it. Don't want to do too many things without testing. Vec. So I'm going to make angle for radians, and I'm going to make angle D for degrees. And there's some functions, some handy-dandy functions already built into Python in the math library for calculating angles and such. So you remember the formula of a dot product, if you've taken vector calculus or physics or whatever, is the dot product is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. So if you solve for everything, the dot product divided by the two magnitudes is equal to the cosine of the angle. Take the inverse cosine of that, and you'll have the angle. So I'm not gonna write that out, go super deep into it, because my job isn't to teach you calculus right now. We're just programming a module for it. So the angle between them is math.a cosine, arc cosine, or inverse cosine. Well, I had a teacher that would get really mad if you said inverse cosine, because technically it's not the inverse cosine. It is the arc cosine. Okay, so we're going to take the inverse cosine of the self.dot product divided by the two magnitudes multiplied. So I'm going to put those in parentheses because order operations is important here. Self.dot magnitude times vec.magnitude. Okay, there we go. And this will return math dot, and so cosine will return it, a cosine will turn it in radians. So for angle and degrees, well, there's a handy function called math dot degrees, okay, that just turns radians into degrees, and I can just put in self dot angle, what is returned from that. So wow, 2 quick little one-liners for that. Okay. Now if I want to throw in parallel, all I gotta do is I gotta check if the angle between them is 0. For vectors, of course. Now I'm gonna do line, modules in a bit, but that doesn't always mean they're parallel, of course. Because you can move vectors around, it doesn't change them, but lines moving them around totally changes them in a sense. It changes their equation. So I'm going to say return 90, because the angle between them is going to be 0. So in this case, it'll be 0. Here, I'll do angle is equal to, I'm going to do angle D, vec. So I like working with that. You can do either one, because the angle in radians and degrees, if they're parallel, is 0. So might as well just do angle. Okay, so return an expression. So the angle between them, it's going to look exactly like this guy, basically. But instead of testing whether the dot product is 0, we'll test if the angle between them is 0. So if it's supposed to be 0, 0 plus tolerance. So it's got to be less than that. It's got to be less than 0 plus tolerance. Angle. And never switch that back to and. Good thing I saw that. 0 minus the tolerance. It's got to be greater than. Okay. We'll just return that expression. Should we have it equals to? It depends on whether you want. I'll throw in equals to. You don't necessarily need equals to here. It depends on whether you want that exact tolerance to be called or have it be within that tolerance. It's up to you. But I'll just throw it in there. Who cares? Now to print some beautiful text. So I'm going to comment out our old test, and now I will go print. So these guys here, a really quick way to make 2 vectors perpendicular is if I have one vector, I just put the opposite like that, and then just make one of them negative. Right? So these guys, when you dot product, you see I get 3 times 4, 12, plus 4 times negative 3, negative 4, 0. So, let's check time. Oh, we're doing all right. So, let's do it. Let's print vector 1 dot product. It's getting dark. Let me turn on the light. Yeah. Alright, sun's setting. Vector 1 dot product. Vector 2. Alright, that should be 0. And then we will print, so they're perpendicular. So vector 1 dot perp. So this should return true. And then I'll make a vector 3 is equal to vector. What should we do? Let's just do 1, 2. Vector 3. Vector 1 dot angle. And we'll do angle in radians and degrees, just to make sure those are working. Vector 1 dot angle D vec. It's not supposed to be just vec. Vector 3. Okay. In fact, let's make this guy parallel. Let's do that. Make them parallel, but make them the exact same vector. So these both should return 0, and then we'll do print vector 1 dot parallel vector 3. Okay. Whoops. Right. Have a little error somewhere. Oh, yeah, right. Parentheses. Because it's a function. Where? My B. Oh, hashtag method. Oh, so it's magnitude. We got a couple errors. We're just gonna knock those guys out. Used to have them as fields, but in the first video I explained why we don't have them as just straight up fields. Tolerance. Spelling names wrong. Oh, right there. Sorry for all these errors, just gonna knock them out real fast. You guys probably spotted all of them. Alright, cool. So we get the dot product, it should have been 0, sweet. Are they perpendicular? It said false. Uh-oh, not good. Alright, so we'll check that out in a sec. The next guy, oh, is it parallel? True. Okay, cool, nice. And the angle between them, 0 and 0? True, that's what it's supposed to be. Alright, we'll deal with perp in a sec. We'll deal with that in a sec. Let's just test this guy to make sure the angles thing are working, because they should have like a random angle. Let's do 7. Let's do something crazy. Alright, yeah, they're obviously not parallel. Sweet. That looks like a good conversion. Okay. Alright. Oh, let's make them anti-parallel. Let's see if that works. What if we go -3, 4? Does that make them anti-parallel? I forget. Let's check. It doesn't. Let's put -4 there. Does that make them anti-parallel? Yeah, it's 180 degrees between them. Okay. So, we will put... If they're 180, they're still technically parallel. So we will copy this bad boy over. And we will slap them down, and we will go 180. Okay? False 180 still. Means it's probably not within our tolerance. Well, I'll pause real fast, figure out what these deals are, be right back. Hey guys, I recorded myself programming the rest of this, or recorded myself talking, but got to film it. I have the completed code. Just noticed that. Yeah, so we didn't add much more. The error, I remember that I left off with you guys, was basically, where are they? For this, I was working with radians because I had angle, and so I needed angle D if I'm doing 180, right? 0, it didn't matter, but 180 it does. Because when I just do angle, it's spitting back pi instead of 180, right? Angle D will spit back 180. And then for perpendicular, it was just a sign flip. It was just facing the wrong way. Just needed to be that way, okay? So I added in 3 new things, cranked them out real fast. I mean, me talking about them will now probably shorten the video a little bit. But here we go. They were the cross product, okay? I just simply used the formula, which is, you can read it right here. But to make it a little bit easier, I just assign these 3 variables to the coordinates from self.core and these 3 to the vector that we're crossing it with, okay? These 2 functions are one-liners, but they're very important, actually. This one is the scalar component of a vector on another. I like to think of that as if I have 2 vectors, and it's high, noon. If they're perpendicular, there's no shadow on the other one from the big guy, right? But the more I tilt him, you see his shadow starts to come down, right? The more there's going to be a shadow, and the length of that shadow is the component of this guy on him. If you've ever taken physics, it's like if you shoot a projectile and the x component of the velocity, right? Something like that. To do that, quick and dirty way, you see the formula is a dot b over the magnitude of a. Well, you could also kind of factor that out and rearrange it a bit, and you get, it's the dot product between the 2 of the guy that the guy on top that you're tilting over with the normal vector of that guy, the unit vector, the guy in his direction, right? So you can just dot them together, and it'll give you the component of this guy that's being tilted on him, right? To find the vector projection, you just take the that scalar multiple you get back, or the scalar version of the component, and you just do you scalar multiply it with the normal vector of the guy. So if I find the component, the shadow, and then I just, the length of it, and I just times it by a magnitude 1 vector, the unit vector in that direction, I'll get the full length vector of the equivalent of how long the shadow is. I won't get the magnitude, I'll get an actual vector that tells me the length of that shadow by taking the component of that shadow, its length, and dotting it with a unit vector. That's along that line as well. Don't think I added anything else in. I think that's it. Yeah, maybe there were a couple errors. No? Alright. And then we just had a test for it. One test that we notice if we run. So cross product, if I cross product two guys that are only in x and y direction, it'll give me a vector perpendicular to both of them. The only way I can get a vector perpendicular to both of them is, in this case, is if I have a guy in z, which is what we get. Okay? Because, let me look. And then if I were to find the component of vector 1 onto vector 2 and the vector projection, well, you notice they're perpendicular, right? So at high noon, there's no shadow falling on them. So this should be 0. We have a number here, but if we look, it's e to the negative 16th. That's hardly anything at all. That's like nothing. All right. So, but that's a problem because we do want it to be 0. So next video, we're going to add in a bunch of error handling, like for example, the 0 vector is perpendicular and parallel to everything, but if we do some stuff where we say we try to find the component on the 0 vector, well, we may at some point, like when we're normalizing, divide by 0, and that's no good. It'll break everything. So we're going to add in a couple error handling. Make sure you put in valid things for coordinates. Make sure you check for 0 vectors. Just type error, stuff like that, and it'll be probably pretty quick. So that's all for this one. Hope you learned something new. Hope you have fun with what we're doing. I'll see you next time.